Welcome to the second video in our 4-2 video series. In video 2 we're going to take a look at simplifying radicals. So in video 1 we took a look at how to multiply and did some of the basics of multiplying radicals. We hinted then that we're going to have a process for simplifying radicals that we would need to do. In this video we're going to take a separate look at simplifying so that we can get the basics of it down, so that in video 3 we can combine multiplying and simplifying. So we're going to have a set of instructions that we're going to follow to help us find the simplified form of a radical. Our first step is going to be completing a factor tree for the radicand. Remember, the radicand is the number that is underneath the square root. In this case it's going to be 18. So I am going to go ahead and move this over here just because I write a little bit big and I want to make sure that you guys can read this. But we're looking at the square root of 18. 18 is going to be our radicand. So what we want to do is to come up with some numbers that are going to multiply to give us 18. Our end goal is to have a list of numbers that cannot be broken down any further that multiply together to give us 18. So just a word of advice on this. Every factor tree is a little bit different because there are different ways to multiply to get numbers like 18. You might have something that looks a little bit different from your partner starting out, but by the time that you get to the end, you guys will have the same numbers as the basis for the factor tree. So let's go ahead and begin. If I'm looking at 18, I'm thinking about what can I multiply to get 18. The first ones that come to mind for me are 6 and 3. Now, I could have also done 2 times 9. That would have given us 18, and we could have started our factor tree there. But I already wrote down 6 and 3, so let's start with that. Now, the bigger the number is, the more different combinations that are going to be able to multiply to give you that number. My advice is to try and find the two factors that are the closest together. That way, you're going to have less steps in your factor tree. Now, just some words of advice. If it's an even number, at the very least, you can always divide it by 2. But that's going to give you another big number on the other side. So something that's really spread out, we're going to have more steps on. If we can get things that are closer together, like in this example 6 and 3, we're going to have a few fewer steps in our tree. But either way, we'll arrive at the same answer. So if I'm taking a look at this, I will now have 6 and 3. So I need to see if either of these can break down further. Now 6, of course, is 2 times 3. Now 2, we can't break down any further. We can do 2 times 1, but that's just going to give us another 2 down here, and it's not going to become any simpler. So what I'm going to do, since 2 does not break down, is I am going to circle that. The same case is going to be with 3. 3 will not break down, so I'm going to circle that. And that completes that side of the factor tree. On this side, we only have the 3 left, and like we just said, 3 cannot be factored. The only thing we can multiply together is 3 and 1. So I'm going to list out in my next step what my simplified numbers are. I had a 2, a 3, and a 3. If it happens more than once, we're going to put it down however many times it occurs. Now in step 2, we're going to identify any pairs of numbers. And these are going to signify a square factor. So what we want to do is look for any pairs that we have. We only have 1, 2, so it doesn't have a partner, it doesn't have a pair, so we're going to leave it alone for right now. The 3's, however, both are going to be a pair. We have 2 3's, that makes a pair. So we're going to go ahead and circle those. These are going to be our square factors, 3 and 3. Now what we want to do now is to break the radicand up into the square factors and the non-square factors. So we're going to take, remember this was the square root of this, we're going to take the square root and we're going to split it so that instead of being one big radical, we're actually going to have 2 smaller radicals that are going to be multiplied together. So we're going to take the one that was not a square factor, 2. He was all by himself. He's going to stay under this one. If we had multiple ones that did not have a partner, let's say we have 5 that didn't match up, he would go underneath there as well. And then under here, we're going to put the ones that are going to be the pairs. So the square root of 3 times 3. Our next step is going to be to pull perfect square roots out and multiply them by the radical. And this is going to give us the new coefficient. Remember, square roots are the inverse operations of squaring something. What we are really asking when we ask for the square root is what two numbers can we multiply together to get that number. So that's why we're looking for pairs. Our square root of 2 did not have a pair, so he is going to still be hanging out under the radical. But here, where we have the square root of 3 times 3, we're asking what numbers would we multiply together to get 3 times 3. That, of course, is going to have to be 3. We have it right there written out. So because we're taking the square root of this, we're just going to move the 1 3 to the outside, because we're saying 3 times itself would give us 3 times 3, which is what we had underneath the new radical. So our answer is going to be 3 square roots of 2. Alright, let's take a look at another example. In this example, we're going to have a variable underneath our radical as well. So we still want to start out with our factor tree. We're going to make a factor tree of 100. We're going to break that down. We could do 10 times 10 to get 100. Those both break down further. 10 would be 2 times 5. Of course, 2 doesn't break down anything further. And the only thing that we can multiply together to get 5 is 5 times 1. So that's as simple as we can go. And we're going to end up with the same thing on the other side, that we're going to break it down into a 2 and a 5. Now, we have the x cubed term to deal with as well. If you think about what an exponent means, it means we're multiplying that times itself that many times. So in this case, we're multiplying x times itself 3 times. So x cubed is the same thing as x times x times x. So I'm going to look underneath my radical, and instead of writing 100x cubed now, I'm going to write what I got from my two factor trees. I had 2 2's, I had 2 5's. Let me erase that and put what it's supposed to be. So 2 5's, and then I had 3 x's as well. So I'm going to write x times x times x. And I'm going to do the same process of trying to find pairs. I have a pair of 2's, I have a pair of 5's, and I also want to look at my variables and see if I have pairs there. I do have a pair of x's. So what I need to do now is I have identified my square factors. I have my pairs of 2's, my pairs of 5's, and my pairs of x's. And I need to break up this radical. I put first the non-square factors, which in this case we only had x. And then I'm going to break up each of the square factors. I had 2's in pairs, so those are going to go together underneath a radical. I had a pair of 5's, so those will go together underneath their own radical. And I had a pair of x's. Remember, when we take the square root of each of these, it's going to make one of them go away. So in the front, I'm going to have 2, I'm going to have a 5, and I'm going to have an x. And all I'm going to do is multiply all 3 of those together. And then underneath the radical, the only thing left that didn't have a pair is going to be x. So I would do 2 times 5 is 10, and 10 times x to give me 10x. So my final answer would be 10x square roots of x. And I'm going to write that a little bit cleaner so you can see it. That got a little chunky there, but there you have it. Now, I do want to point out one thing. Sorry, the battery's running low. I'm trying to milk the last bit of it here, so ignore that pop-up. But if we were looking at this, we could have taken a slight shortcut with this. When we broke down 100, our very first step was multiplying two numbers that were exactly the same. What that means is 100 is a perfect square. We have two numbers that multiply times itself, 10 and 10, to give us that number. If we would have seen that that was a perfect square there, we could have taken out breaking it down further and done a pair of 10's instead of doing the pair of 2's and the pair of 5's, and we could have cut out one step there. We did include in Appendix A a list of perfect squares to help you identify some of these, and maybe those will help save you a little bit of time as you go through doing these factor trees. And give the U-try problems in the 10th. Alright, see you in the last video.